Greetings to all my tech heads out there in the KevTechify nation. And if you're new here, welcome. In this episode, we're going to look at point-to-point OSPF networks. We'll be discussing the network command syntax, the wildcard mask, passive interfaces, OSPF point-to-point networks, loopbacks, and finally, point-to-point networks. This episode is part of my series on enterprise networking, security, and automation. I'm Kevin here at KevTechify. Let's get this adventure started. A point-to-point network is that connection that goes from one router to another router. No other devices can connect in there. Typically, this is represented by a serial connection. Serial connection is a point-to-point. Sometimes you can use an Ethernet port to do a point-to-point connection, but that cable needs to run directly from one router to another router. You can't run it from a router to a switch to a router, because as soon as you connect it to a switch, you can connect other devices into that little network. It needs to be a point-to-point connection where no other devices can come into that network. Now, how we go about and configure our interfaces is we use the network command. In OSPF, we configured those interfaces that belong to that point-to-point network. You can use the network command, or you could go into that interface directly and use the IP OSPF command. Basic syntax here for the network command is you have to get into the configuration of your routing settings. So from global configuration, this router OSPF, and then your process ID. Once you're in there configuring your OSPF settings, then you can use the network statement. The network address, once again, the network address ends in zeros in binary. Then we put in the wildcard mask, and that's something a little bit different than the subnet mask. Then we tell you what area it belongs to with the area ID at the end. Now, this network and wildcard mask, this is the syntax that is used to enable OSPF on interfaces. Any interface that matches this, they're enabled to send OSPF packets. And so the network address needs to contain the IP addresses of the interfaces. When it does, then we can send and receive OSPF packets on those interfaces. Area ID refers to the OSPF area it belongs to. That area ID can be any value, but it has to be the same on all routers in your OSPF area, so they all need to match so they know they can communicate. Typically, in a single area OSPF version 2 network, the best practice is to use area 0. Technically, you can use anything, but best practices is to use 0. The wildcard mask is a little similar to the subnet mask, but yet it's completely different. The wildcard mask allows us to identify the difference between the network portion and the host portion. It draws that line in binary. That network, that subnet mask and the wildcard mask, they're 32 bits long. They're one number followed by another number. Subnet mask is all ones followed by zeros. Wildcard mask is all zeros followed by ones. Some people go, well, if they basically do the same thing, why do we have two separate ones? From what I've been told, it comes from way back when they first started doing this, when processing power was at a premium, that the wildcard mask technically takes a little bit less processing power, can be processed faster, giving you quicker results. But in today's world, with our modern processors, that difference really is not noticeable, but it's embedded into that into the Cisco operating system where we need to do that. To figure out what the wildcard mask is, a lot of people say the easiest way is to take 4 255s. Go ahead and write out 4 255s, 255.255.255.255. Then write your subnet mask below it in dotted decimal notation. For this, we're going to use a /24, and that's 255.255.255.0, and then we subtract those. And in the first octet, we got 255 minus 255 gives us zeros. Second octet, 255 minus 255 gives us zeros. Third octet, 255, 255 gives us zeros. And then in the last octet, 255 minus 0 gives us 255. And that gives us our wildcard mask. It's the inverse of the subnet mask. It's the exact opposite. Ones and zeros are changed. If we would write this out in binary, we'd write the subnet mask out. We'd write out 8 ones here, and we'd have 8 ones here, followed by 8 ones. Yeah, I know it's probably not 8 ones. And then followed by a bunch of zeros. Then we'd go and we'd write the subnet mask out. Actually, let's go ahead and write the 255s all out in ones here. I got third octet of all ones and the fourth octet. 1 minus 1 here gives us all zeros in the first octet. 1 minus 1 in the second octet gives us all zeros here. In the third octet, we have 1 minus 1 that gives us all zeros. In the fourth octet, we have 1s minus zeros that gives us all ones here. All ones is equal to 255. We convert this all into decimal. That's how we get it. A lot of people use the shortcut method over here. Now, let's take a look. Instead of doing something on the class full, let's do something on the class list. Let's take /26. Let's take a /26. What we do is we write down our 255s for the 4 octets. Then we write down our subnet mask in dotted decimal notation. A /26 is 255, 255, 255, .192. We're borrowing 2 bits, a 128 plus a 64, that gives us 92. And then we subtract them. And subtract the first octet, 255 minus 255 gives us zeros again. Second octet, 255 minus 255 gives us all zeros. Third octet, 255 minus 255 gives us all zeros. And then the last octet, we start off with the 255, and then we minus that value of the subnet mask of 192. So 255 minus 192, that gives us 63. Our wildcard mask from a subnet of 255, 255, 255.192 is 0.0.0.63. I'm going to take a second and I'm going to draw this out in binary to show you. The first 3 octets here, I'm going to say are fairly easy to see. You have all ones here. You have all ones here. Subtract those out, that gives us zeros. But in the last octet, this is where it gets a little bit more confusing. In the last octet, for our 255s, we have 8 ones. So that's a 1, 2, 3, 4, 5, 6, 7, 8. That gives us 8 ones. But to get 192, that's our /26. There's 2 bits that are a 1, and then the rest are zeros. That gives us a 1, followed by 6 zeros. Trying to line them up best I can. Then we subtract those. When we subtract those, what we get here is that first bit. We get 1 minus 1, that equals a 0. Then we get 1 minus 1, that equals a second 0. Then we get a 1 minus 0, that gives us 1. 1 minus 1, that gives us another 1. 1 minus 1, 1 minus 1, 1 minus 1, and 1 minus 1. The binary result of 255 minus 192 is 0, 0, 1, 1, 1, 1, 1, 1. 2 zeros, 6 ones. Convert that into decimal. We have our values here. We have a 1, a 2, a 4, a 8, a 16, a 32. Add those up, that gives us 63, which is this value here. It's the opposite of that subnet mask. That's how we calculate the wildcard masks. If you like this episode on Point-to-Point OSPF Networks and you get value out of it, and depending upon the platform you're using, please click that like button, give a 5-star rating, leave a comment. Doing this supports the channel, which in turn helps me bring you more great content. Subscribe to my channel and click that notification bell. You can also visit my website at KevTechify.com for all of my details and how to get these episodes in video and podcast form. When we configure OSPF using the network command, there's two ways where we can do that. We can either specify the network address, and that network address has to include the IP address of the interface you want to run OSPF on, or you can include just the IP address of that interface. In the first example here, we go into the OSPF configuration, process ID 10. Now we can add in our network statements. We're adding in the network, and then notice we are actually adding in a network address, not an IP address, a network address. How do we know it's a network address? Network addresses end in zeros. And then we have our wildcard mask. Our wildcard mask says that we have zeros followed by 255s, the opposite of that subnet mask. Any interface that has an IP address that matches this, so any address or any interface that has an address of 10.10.10.1 and then .1 to .254 would have OSPF configured on it because it fell into this range, and then your OSPF area is 0. Then we come down here to the next one where we include the 10.1.1.4 network. Yes, that is a network address because we're using that /30 there. Specify our wildcard mask. So based off of that /30 subnet, you calculate out your wildcard mask to be 0.0.0.3 and say, I want this to be in area 0. And then finally you do that last point-to-point connection here, 10.1.1.12, that has a /30 network. Calculate your wildcard mask, comes out to 0.0.3 and on area 0. That'll set up those 3 interfaces from R1 to work with OSPF. The other way to do that is to specify the IP address of the interface, not the network address that IP address on the interface belongs to, but the actual IP address of the interface. We can go in to the router OSPF configuration. We can put in the network statement. It's a network statement, but we're actually going to specify an IP address. We come in here, we specify the IP address of 10.10.1.1, and then we specify 0.0.0 as our wildcard mask. Remember, wildcard is the inverse of our subnet mask. So the inverse of 0.0.0 wildcard is 255, 255, 255, 255, 4 255s, meaning match every one of these 32 bits here. So wildcard mask of all zeros, subnet mask of all 255s means match all 32 bits of this address. That is the address we're using. And so it's going to take and say, okay, the interface that has this IP address, you're going to be in area 0 for OSPF. Look and see what's happening up here. First example, we used the network address where it was 10.10.1.0 with a wildcard mask of 00255, meaning anything in the 4th octet is our host portion. Down here in the second example, that network portion is the same. These two network portions are the same. Same way to specify the interfaces, same interface, just 2 different methods. We can continue in our second example. We specify the IP address of that point-to-point connection with all zeros here, saying you're going to join 000, and that third interface, IP address, zeros, area 0. Some people argue that the second method is easier, using the IP address and the wildcard of all zeros. Why do they say that? You don't have to calculate the network address that ends in zeros. You don't have to calculate this part. And then you don't have to calculate the subnet mask. Because down here in the second example, you put in the IP address and then you put in the wildcard of all zeros. There is no calculating. A lot of people use this method, but you can use the network address with a wildcard mask. You can also set up OSPF version 2 using the IP OSPF command. In our example here, I want to show you first how to remove those network statements we previously set up. Go into your router, go into the configuration of your routing protocol, OSPF 10 here, that's that process ID. And then instead of putting in your network statement like we did there, and so our network statement was the network, the IP address, followed by all zeros, and then our area ID, you put the word no before it, and that removes them. Once you have them removed, we can then start using the IP OSPF command to signify what interfaces are participating in OSPF. To do that, and this is my preferred method, I like doing it this way. That way I know the interface I'm on is using OSPF. You go into the interface first. In this example, we are going to go into the interface of Gigabit Ethernet 000. So we're going into gig 000. Once we're in that interface configuration mode here on R1, we can go ahead and put in the IP OSPF command. Now, how this command flows is IP, because it's part of the IP version 4 suite. We're dealing with the OSPF routing protocol, so we start off with IP space OSPF. Then we have that process ID. Remember, that process ID is locally significant to the router, but it's a best practice to use that same process ID on all of your devices. And then after we say our process ID, we need to say what area, what group of devices are going to share data back and forth. And because we're only running a single area OSPF, it's going to be the same. And for us, it's area 0. With this method, we don't have to worry about IP addresses, network addresses, wildcard masks, subnet masks. We don't have to worry about any of that. We just go into the interface and say, okay, this is your OSPF process ID, and you're going to operate in this area number. That's all you have to do. I like this method the best. And to configure and to continue configuring through our example here, we go into the second interface, Gigabit Ethernet 001. We say, okay, you're going to be using OSPF process ID 10. Once again, that's just locally significant to the device, but good practice to use it all throughout your network. And then you will be participating in area 0 for our OSPF. And then we do the last interface, which happens to be our Loopback 0, and we enter in the same command again. Same process ID, same area ID. When you configure OSPF, OSPF messages are forwarded out all OSPF enabled interfaces. Every interface that matches those statements you just entered in to set up OSPF there, OSPF messages are going to be sent out those. This could cause some congestion on your network because you only need to send out OSPF messages to devices that will accept or need OSPF messages. An example here is we have our 3 routers, right? And we have the Loopback interface that comes off of it that represents another local area network. You don't have to send out OSPF messages out that interface, but OSPF needs to be enabled on that interface to route traffic to it. Did you catch that? On that Loopback interface, OSPF needs to know that that network exists so we can route traffic to it, but you don't have to send OSPF messages out there because there's not another device on that network that needs those OSPF messages. And what we can do is we can turn that into a passive interface. It participates in the routing, we know it exists, but we don't have to send OSPF messages out that way. Now, Reasons for not sending that out is it eats up our bandwidth. It uses up our precious bandwidth. It uses up precious resources. We don't have to worry about giving more processor, more RAM to send out those unneeded messages. Plus, it's an increased security risk. Somebody could intercept those messages and, in theory, figure out what your network topology is, maybe figure out a way to change the routing tables, make your network not work correctly. It's just a security risk. You configure these passive interfaces. Here in our example, we come into the configuration of our routing protocol, OSPF10, and we say passive interface, and then what is the name of the interface? In this example that we're working through, we're going to say our passive interface is Loopback 0. That represents that LAN that is outside the triangle of those 3 routers. When we do that, we can give you a show IP protocol statement. We go through, we see lots of information, and then towards the bottom, it'll list our passive interfaces on our router. Here it says our passive interfaces is our Loopback 0. That is what we configured right here. Once again, that represents that local area network that probably has PCs, devices, printers all on it, but it doesn't have another device that needs OSPF, so we don't have to send OSPF messages out that interface. By default, routers elect a DR and a BR, a designated router and a backup designated router on OSPF networks, on Ethernet. Even if there's just 2 devices on a point-to-point connection, take that point-to-point connection from our example between R1 and R2. There is just 2 devices. There's going to be an election process to figure out who is the designated router, who is the backup designated router. We can confirm that. We can do a show IP OSPF interface on gig 000 from R1. That is the connection to R2. So this is the connection to R2 here. It's a point-to-point connection. There's only 2 devices on there. The IP addressing will only allow 2 devices. We can see as we do this show IP OSPF command here that we do have a network type of broadcast. So we are broadcasting information. And then down here, it completed the election. The designated router ID is 2.2.2, and remember, for router 2, that's what we set the router ID is, 2.2.2.2, so we could easily remember it. And then the backup designated router ID is 1.1.1. That's for router 1. And those are the only 2 devices on there. It gives us the interfaces that they're connected to here also, but it's showing us that both of the devices participated in that election. One of them got the designated router, the other one got the backup designated router. To stop this election process, to stop it on this point-to-point network where there's only ever going to be 2 devices, we don't have to have that election process happening, is we can turn that interface, we can say this is a point-to-point connection. What we do is we go into the configuration of the interface. Here we go into interface gigabit Ethernet 000, and then we use IP OSPF, the network command, and then we use the option to say that this port for an OSPF network is a point-to-point connection. When we do that, the interface goes down, comes back up. It goes through that full process of OSPF until we get to the full state. That's when we're fully converged at that point in time. If we do the show IP OSPF interface command here, it'll give us the information. Here we have our gig 000, one we just set as a point-to-point in OSPF. We have our process ID of 10, the router ID of 10, 1.1.1, we're on R1, and then it says network type of point-to-point. that signifies that this is a point-to-point network. We don't have to do that election. There won't be a designated router. There won't be a designated router on this connection because there's only 2 devices. There only will ever be 2 devices. When you configure a loopback address, that loopback address is configured as a host route. It's configured as a /32, meaning it matches all 32 bits. We configured a loopback interface of the 10.10.1.1 on R1. OSPF will advertise it, and then on R2, when we do a show IP route on R2, that network comes up here as our 10.10.1.1 and then a /32, meaning this is a host route. This is for a single host. Now, if you want to advertise this as a full local area network, a full network, instead of just one IP address, maybe a range of IP addresses to help you give some flexibility for what you're doing, what we can do is on R1, we go in and we go into the interface here of Loopback 0, and we change that to a point-to-point network. When we change that to a point-to-point network, it then goes and gets advertised as a network address. To show us how we can do that, to verify it, we go back to R2 here. We do that show IP route again, and we can see here that now instead of matching all 32 bits, we just match the first 24 bits. We look at that network portion. That will help give you some flexibility or whatever you need to do to match it to your needs for your network. It was my pleasure to provide you with this wonderful episode on Point-to-Point OSPF Networks. If you like this episode and you got value out of it, and of course, depending upon what platform you're using, please click that like button, give a 5-star rating, leave a comment. This all helps me bring you more great content. Please take a minute to subscribe to my channel. All of my socials and contact information are on my website, KevTechify.com. You can get all of these episodes in video and podcast form. In the upper right is my playlist for my series on enterprise networking, security, and automation. In the bottom right is another one of my favorite episodes that I linked just for you. Thank you so much for watching this episode on my series of enterprise networking, security, and automation. Once again, I'm Kevin. This is KevTechify. I'll see you next time for another great adventure.